Hello. In this lesson, we look at another brute force algorithm for searching. But in this case, instead of searching for numbers in an array, we are given a pattern that is a string, and we have to see if that pattern occurs in a longer string. This is called the string match problem. So the string match problem it's also known as substring search. So you're given a longer string and you're looking for a substring in that string. In a sense, in a very crude sense, what search engines do is exactly solve this string match problem. When you type in a keyword into a search engine's search box, that is the pattern you are searching for, and the longer string or the text in which you are searching is typically an entire document or a web page and so on. Of course, a brute force algorithm for doing that would be extremely inefficient, but nevertheless, it is the search engine problem is a string match problem. So we are given a text T, let's say its length is n, and we are given a pattern P, let's say its length is m, and m must be less than or equal to n. If the pattern you are looking for is longer than the text, then the text could never contain that pattern as a substring. So obviously m must be less than or equal to n. Typically it is much less than n. So you're given a text and a pattern. Both are strings. And typically the pattern is a shorter string than the text. And the problem is to find whether the pattern is a substring of the text. That is there a position I in the given text T, starting from which the entire pattern P occurs in the text, right? So let's look at an example to make that clear. And of course, we are going to consider a brute force algorithm in this lesson. Now, one of the things before we even look at the example is a partial match is not good enough. Let's say the pattern had 4 characters in its string, and only the first 2 are present. That is not a successful search. The entire pattern, right, must be present in the given string. So the entire pattern means a partial match is not a successful search. So let's take this example. You must have heard of this tongue twister called "She sells seashells on the seashore." And let's say that is the text. So this is the text that is given to us, and the pattern that is given to us is shell. We're trying to see if the pattern shell is present in this given string. That is the brute force algorithm we need to construct. So let me write the characters in this given text. So there is she and a space, sells, sea, shells. I will not write the rest of it because we know that at this point we are going to find a match for shell. Now how do we begin? We begin by writing the pattern here, essentially, right? And we find that this part matches the first 3 characters of the given text, but that is a partial match. When we come to this position, we find that it doesn't match, right? So the first part of the text does not match the given pattern shell. Only the first 3 characters of it match. The rest of the other 2 characters L and L do not match this white space and S. So now what do? We need to look for another position in the array to start doing this comparison in the text, I mean. So how do we do that, right? In a smart algorithm, you might do something like, let's look for the next occurrence of S, because the first letter of the pattern is S, right? Here we don't do anything like that. We simply advance it 1 position, and I write shell here. Now the very first letter does not match in this case. This is S, that is H, right? So what do? I advance it by 1 more position, and I write shell here. Like this, we advance by just 1 position each time, right? When you come under cell, right, here, when I write shell here, what happens? The S matches, right? Until then nothing else had matched, but the H and the E don't match. This E doesn't match this H, right? So we fail again. So we keep doing this. Once again, when we come here, right, this S and this S will match, but this E and the H won't match. Finally, when we come here, you will write shell here, right? All of the 5 characters will match these 5 characters in the string. Then the algorithm returns the index of this position as the answer, as the return value for the successful search. So again, what we do is we start at the beginning of the text and we compare the pattern to the text at that position. If the entire thing matches, we have found a successful search. Otherwise, we simply advance without doing anything smart. With a brute force, we simply advance the position by 1 and start comparing again. So in the worst case, you may have to compare at every position in the given text, right? But you will also notice that each of the comparisons is not a single comparison like we did in the case of sequential search, where we were searching for a number or some other data, simpler data element which can be compared in a single step. Here we are doing string comparisons, or in other words, each of the m characters of the pattern must be matched to the corresponding m characters of the text until either everything matches or you find a mismatch. So in this case, for example, we made 3 comparisons, S, H and E. Then when we made the 4th comparison, we found a mismatch. In this case, in all these other cases, a single comparison gave us a mismatch. In this case, we did 1 successful comparison and the 2nd comparison gave us a mismatch. Finally here, all 5 comparisons were successful, right? And we found the answer. So as we do the analysis after writing this algorithm, it's important to remember that in each position in the array, we may do up to m comparisons because the pattern is of length m, right? Up to m comparisons may have to be made at each position in the array. Right? So now let's try to write the algorithm for string match or substring search. So as I said, the idea is in every position of the given text T, do the next m elements of the array or the text match the m elements of the pattern P in the same order, right? And if there is a match, we have found a successful search. Otherwise, we advance the position and repeat the matching process. So the algorithm string match takes 2 inputs, the text of n elements and the pattern of m elements. So T is from 0 to n minus 1, P is from 0 to m minus 1. The pattern, and as I said before, m must be less than or equal to n. So we start at the beginning of the text, I equals 0, right? And we go till the end. But not exactly till the end. We don't go till n minus 1. We only go till n minus m, right? Why is that? Because if you are looking at the end of the array and the last, there must be m elements to compare to the pattern. There is no point going beyond that. So your array is text T is going till there, right? This is T and this is the pattern P, which is of length m. So this position is your n minus m, right? So we only need to go from 0 to n minus m. There is no need to go beyond that because this pattern itself is of length m and we should be able to match it to the remaining characters in the text T. So it is from 0 to n minus m, not 0 to n minus 1. What do? We start at the beginning of the pattern. So I is the index into the text and j is the index into the pattern P. So j equals 0. While j less than m, that is while we have not exhausted the pattern, and the jth character in the pattern is equal to the I plus jth character in the text, right? We increment the index into the pattern, right? So for example, here we had shells in the text and we have shell in the pattern. So I will start here, j will start here, right? Now what happens? Pj is, in this case P0 is S and T of I plus j, right? So that is S and these two are matching. Now we only advance j, I remains here, right? j advances to the next one, and p of j is h, and t of I plus j will point to h. They match each other. I remains the same. I is in the outer lobe. J keeps advancing, right? And with each advancement of j, we compare the jth character of the pattern to the I plus jth character of the text, and if they keep matching, we keep advancing. So once you come out of this loop, what will happen? This loop will exit because j is less than j must be less than m. So when j becomes equal to m, you exit, or when there is a mismatch between pj and ti plus j, then also exit. So the loop condition, both of them must be true. J must be less than m, and the character in the pattern must match the corresponding character in the text. When either there is a mismatch or you have come to the end of the pattern, we exit from the loop. When we exit from the loop, if j equals m, that means there was no mismatch, right? This condition was satisfied throughout the pattern. That means we have found a successful match between the pattern and the text, right? So we return the successful search index I as the position in the text where the given pattern P occurs. If on the other hand, right, j is not equal to m, then what do? Right? We go back and continue the for loop. Right? You notice that that is inside the for loop. So you go back and continue the for loop, increment I, and repeat the whole process, like we saw in the example of she sells seashells on the seashore. So you go through the entire loop. At the end of the loop, if you never found a successful match, if j was never equal to m and you could never return I, then the search is unsuccessful and we return -1. So this is the string match brute force algorithm. So the outer loop advances the position in the text, namely I, where we start looking for the pattern. The inner loop traverses the length of the pattern, right? So this loop is executed at most m times, right? This comparison pj equals ti plus j is done at most m times in the inner loop. The outer loop executes how many times? Right? From 0 to n minus m. So it is n minus m plus 1. That is the number of steps the outer loop is executed. Right? So that's how the string match algorithm for brute force algorithm works. So how do we analyze its complexity now? Right? The inner loop executes at most m times. The outer loop executes, right, n minus m plus 1. Since m is less than or equal to n, right, this is, in the worst case, this is also of order n. So you are talking about the complexity of the algorithm being n into m. N into m times is the worst case scenario. That's the complexity of the string match brute force algorithm. Why is that so? Because you are required to advance the position in the text an order of n times, and for each of those positions you may have to do m comparisons. So the worst case scenario is one where, right, every position there is a match of m minus 1 characters, right? And even in the last one, only m minus 1 parts of the characters in the pattern match the given text. There is never a complete match. So on an average, the performance may be much better. In fact, you can show that for random texts and random keys, right, the average case for this algorithm is just theta n plus m, not n into m. But that happens so because you will never find the worst case when you take random inputs, where in every case you have to do m comparisons. But nevertheless, the worst case complexity of this algorithm is n into m. If m is much less than n, right, then you can say this is almost order n. So for example, if you limit the pattern to be less than or equal to 10 characters, say, right, then it becomes ON. It's a linear algorithm. But if the pattern itself can be almost as long as the given text, right, then it is so. For example, if m can be equal to n, then this becomes O(n) squared in the worst case, because n and m are of the same or size. But if you can limit the size of the pattern, if m can be treated as a constant, then it becomes a linear time algorithm. So the complexity of this depends on both the length of the given text and the length of the given pattern. And as I said, in random cases, in average cases, it may be the number of steps required may be much less than n squared or n into m. So that is how string match works as a brute force algorithm. So here is a question. Let's say we make a small improvement to string match algorithm. We don't know if this is a good one or a bad one. Let's try it anyway. What we do is, if there is no successful match at some position I, instead of advancing it by 1, instead of doing I equals I plus 1, what if we did I equals I plus m? So we jump m steps, or we go to jump m steps. That is, the length of the pattern is how much we jump whenever there is a unsuccessful match. Then what happens? Which of the following statement is true? So 3 of the following statements are false, 1 is true. The first one is, it will find a match for the pattern bubble in buggy bubble sort. So this is the text given to you. Second option is, it's a correct algorithm for the string match problem. The third option is, its complexity is now order m, where m is the length of the pattern. And the fourth option is, it will find a match for bubble in bug bubble sort. Which of these is true? Well, option A is true, because what happens is, you start matching BU to this BU, then there is an unsuccessful match because this B doesn't match this G. So now we do I equals I plus m. M in this case is 6. The pattern has 6 characters. So from here we jump 6 steps. 1, 2, 3, 4, 5, 6. Right? So you come to the correct position in this case, and the bubble will match the bubble, and in this case it will actually find a successful match. But this is not a correct algorithm, because as you will see in option D, it will not find a match even when this pattern occurs in the text. Its complexity by no means order m. If m is much smaller than n, it will still be order n into m, or order n itself. So it cannot be order, in the worst case, its complexity is in any case not going to be order m. In this case, it will not find a match, because what happens is, once again, this BU and this BU will match. This B will not match this G. Now we will do I equals I plus m. So I will advance to this position, right? And then this B will match this B. The U will not match this B, and you will return an unsuccessful search, although the pattern bubble is present in bug bubble sort. So this is also not correct. The only correct option is, the only true statement is A. And by the way, let me say it again, this is not a correct algorithm for doing string match. We only considered that option to see what happens. There are more efficient, smarter algorithms for doing string match, which we will study later in the course. Thank you.